This is the third in a series of videos about the equilibrium constant. In the last video, we learned what to do when you want to multiply your reaction by something, or if you want to add multiple reactions together, what the effect on the K value was. And in this video, we're going to introduce a few more bits of terminology and then talk about what the number that you get for K actually means. Okay, so a few bits of terminology that we need to throw in here. We need to differentiate homogeneous and heterogeneous equilibria. Okay, so the first kind is called homogeneous equilibrium, homo meaning the same. So the part that is the same in this equilibrium is the phase. The phases of all the reactants and products are the same here. So all reactants and products are in the same phase of matter. So they can be all liquids, they can be all gases, they can be all solids, probably not, but they could be. Whatever they are, they were the same. And the fourth unofficial phase besides solid, liquid, and gas is aqueous, meaning dissolved in water. Because this happens so commonly that we've just given it its own phase. So here, all of these things are labeled as aqueous. They're all dissolved in water, so they all have the same phase. And just a reminder, there is one more unlisted item here, and that is the part that makes it aqueous. That is the water. But we leave water out of our K expression because it's the solvent. And we said the solvent was present in such a higher concentration than everything else that it doesn't change appreciably, and so it's constant, and we don't include it in the expression. So the water part is left out if we were to write the K expression. Okay, and the other type is a heterogeneous equilibrium. Hetero meaning different. And in this case, there are two or more phases present in the mixture. So it could be any combination of solids, liquids, gases, or aqueous phases. So here's an example of a phase change of bromine, Br2 as a liquid, going to Br2 as a gas. There's a liquid and a gas, both present in this equilibrium. Okay, so now that we know all the words and terminology that we need to know about the equilibrium constant, let's talk about how big that number is, because that number can be anywhere from 0 all the way up to the largest possible positive number that you can think of. But what does the size of that number mean about the concentrations? Because that's what we really want to know. What do the concentrations of reactants and products look like at equilibrium? So we drew a diagram at the beginning on the first page, and we showed the concentration of liquids of the reactant liquid to the product solid. So let's draw a few more of those and outline the different kinds of conditions we can have. So we'll do the concentration versus time again. So let's say we're going from reactant, which we're going to draw in black, to product, which we're going to draw in red. So they look really different. Let's say we have one reaction where we start with lots of reactant and most of it stays. So a little bit of the reactant changes to product, but most of the reactant is still there at the end. That is supposed to be a flat line. And the product starts at 0. Some of it forms when the reactant breaks down, but not very much of it. So there's our product is at a pretty low concentration, and the reactant is at a pretty high concentration at equilibrium, which is the flat part. So we can have a large amount of reactant and a small amount of product present in our equilibrium. We could also have the opposite. If we started with all reactant, all of it could react down to a very low concentration at equilibrium. And when we started with zero product, lots and lots of product could form until we had a much higher amount of product than reactant at equilibrium. And if we mark our flat part, it's probably about here for our equilibrium section of the graph. Oh, and we have to label our axes. Concentration versus time for that one. Okay, so this one had a large amount of product and a small amount of reactant. It's still at equilibrium. It's just that at equilibrium, there is more of the product side than there was of the reactant side. And in this one on the left, there was more of the reactant compound than there was of the product at equilibrium. And so now let's draw one in the intermediate range. We start with mostly reactant, and we lose a lot of it, but not all of it. There's still an appreciable amount of reactant left at equilibrium. And we'll say we started at zero product and we formed a fair amount of product. And we have a fair amount of that present at equilibrium. So at our dashed line, there is a substantial amount of both. And our axes are concentration versus time, as usual. So these are sort of the two extreme cases and a picture of the intermediate case. So for this picture on the left, where most or almost all of what's in the flask at equilibrium is reactant, we say that the forward reaction does not occur. So that reaction that was supposed to make product just wasn't happening. And we say the reverse reaction goes to completion. The reverse reaction is the one that makes reactant. And since we have almost all reactant, we can say that that reaction went to completion or finished. It used up everything available. And this is going to happen in situations where your equilibrium constant K is less than 10 to the negative 10th. So this is 0.000000000 something. So your K cannot be negative number. So K less than 0, not possible. Your K is always going to be a positive number, but it can be an awfully small positive number, indicating that the reverse reaction goes to completion, the forward reaction does not occur, and the final mixture is mostly reactant. Okay, let's look at our other end of the spectrum here. So where we have mostly product present at equilibrium, that means that our forward reaction goes to completion. That's the one that makes product. And the one that uses up product, the reverse reaction, does not occur. It is not a match. So the forward reaction goes to completion, and that means our K value is going to be very large. And we're going to specify that very large is greater than 10 to the 10th, which is 10 trillion, I think, a pretty large number, a lot of zeros there. Okay, so this is going to be our boundary conditions, 10 to the negative 10 and 10 to the positive 10. And so then for our intermediate condition here, K is going to be somewhere in between 10 to the negative 10 and 10 to the positive 10. And I have written K, 10 to the positive 10. And in this condition, we have significant amounts, running out of space here, significant amounts of reactant and product are present at equilibrium. Okay, so significant amounts, reactant and product. So this is important. So if I asked you to draw me a picture of what the concentrations might look like if I had a K value that was greater than 10 to the 10th, you would draw me something where the product concentration was much higher than the reactant. If I asked you to draw me a picture of the concentrations for a reaction where the K value was very, very small, you would draw mostly reactant. And if I didn't specify, you would draw something more like the middle, where there are appreciable amounts of reactant and product present. So this should help you to understand what equilibrium is, when it happens, and how much product and reactant is present for a particular compound's equilibrium at a particular temperature. So in the next series, we will talk about non-equilibrium systems and what happens as they shift back towards that favorable equilibrium position.